Hello, this is EEL6591 Wireless Networks project. My name is Craig Balgobin. Today is April 19th, 2012. The objective of this project is to simulate a QPSK and an OFDM system in MATLAB. Let's look at some block diagrams. Okay, so for the QPSK system, I was able to read in a proprietary bit stream, a file, and go through my process and generate an IQ waveform that was played back on an RF up converter, an RF signal generator, fed into a receiver, and it played audio. These are the steps that I took. You generate bits. You can do it one of two ways. You can read in a file, or you can use a PN pseudorandom number generator in MATLAB. Once you generate bits, you take bits for QPSK. You take 2 bits at a time to form a QPSK symbol. Once you form a QPSK symbol, and you to create the waveform, you have to oversample it, and this oversampling is in anticipation of the pulse shaping filter. What the pulse shaping filter does is it smooths out the transitions in the QPSK symbol and kind of limits the bandwidth. You'll see in the simulation what it does. Next, for the signal generator, I had to normalize the waveform. The reason being is that when it plays back the waveform, the DAC of the SIGGEN, the digital to analog converter of the SIGGEN, sometimes it clips. There's clipping at the DAC, so you have to normalize the waveform. Next, it's passed through an additive white Gaussian noise channel, and then fed into a receiver. For an OFDM system simulation, I just generated random bits, then I did QAM mapping. I used 4 bits per symbol, so 2 to the 4 equals 16. So I used 16 QAM. There's also 64 QAM and 256 QAM. There's all types of QAM. I use 16 QAM. After you generate these QAM symbols, you wrap them up in an IFFT, an inverse fast Fourier transform. After this process is completed, you insert a guard interval. The guard interval kind of lengthens the symbol period to combat ISI, inter-symbol interference. After the guard interval, then you do a transport layer framing, and then pass it through an additive white Gaussian noise channel, and then end result at the receiver. Let's look at some simulations. Okay, so here's my QPSK simulation. We can start that. So what I did was I read in a bit file, a proprietary file, you can see here, and I mapped 2 bits per symbol. So that's why in this diagram you have 4 quadrants. You have in a Cartesian plane, it maps, and it's a very strong, distinct transition. This is why the filtering is needed. So when you apply this pulse shaping filter, it smooths the transition in the waveform and you get the Fourier transform of the filter, which is a sync pulse, is kind of a sync function. The transform of a sync function is kind of a rectangular pulse. So when you apply this filter to a waveform, it smooths the edges and gives you a distinct bandwidth. And here you see the filter. Give you a bigger look at that, and it's just a sync function. And once it passes through, this is the FFT output. So let's show the constellation before and after. On the right is the constellation before filtering. On the left is the constellation after filtering. As you can see, there's a lot of easy transitions, there's a lot of overshoot, and this is what limits the bandwidth in the QPSK system. And here's a scatter diagram of the QPSK symbols, and you can see noise in the in between the quadrants. So after forming my INQ file, I did some analysis on it. I was able to get the crest factor of the waveform, and this is needed for the scaling. The DAC of the signal generator is a 16-bit, so you have to scale it to 16 bits so that it doesn't clip. And here you see where I took the IQ file and this puts a header on it with information like the clock, the playback clock, and the samples, and the waveform length. And I was able to take the file and play it on a satellite radio receiver and get audio with minimal bit error rate. If we look at the analysis, this shows you the crest factor of the waveform. It's just something to show you. Okay, so after I did the QPSK, I experimented with differential QPSK using MATLAB's differential QPSK modulator. Simulate that. So as you see, the scatter plot is a little different. It's phase shifted. Now the reason it's called differential is because it's looking at the difference in the QPSK symbols and then plotting a quadrant. So that's differential QPSK. Next I did rectangular QAM. As I said, a 16 QAM, so it's using 4 bits per symbol. So here's the scatter. Here's the scatter plot of the QAM symbols before filtering. Here's the filter applied, the root raised cosine filter applied. And here is the output of the filter, which you can see the symbols are a little bit, they're not as distinct as before filtering. And here you see the IQ waveform normalized to 1 and an FFT output of the 16 QAM waveform. So then I use the 16 QAM waveform to generate an OFDM waveform. So let's simulate that. So here's the constellation diagram before the inverse fast Fourier transform is done. And as you can see, there's 16. Again, there's 16 points. Here is the FFT, the power spectral density of the OFDM spectrum. And what I was able to do is I passed it through an AWGN channel, a noisy channel, adding, here I defined a signal to noise ratio. So for this simulation I did a signal to noise ratio of 20, which is very good. So if you look at the signal transmitted and the signal received, it's pretty identical in a 20 dB signal to noise ratio channel. If I lower this channel to, let's say, 8 dB, as you can see, there are differences between the signal transmitted and the signal received. This is because I'm using a lower signal to noise ratio, so the signal wouldn't be received as properly with as good a bit error rate as I did with a strong signal. So that's my simulation findings.